welcome back. Uh, what we have studied in the fundamental theorem of calculus is that if f continuous and there is an antiderivative such that this f prime is equal to f, then what we have seen is that a to b f is equal to f b minus of f a. So, let us first do some example and then we will address the question of what is the importance of this condition, what we are imposing that the derivative is continuous. Okay, so, some easy example to compute this, actually this fundamental theorem of calculus gives us, this is a powerful tool to evaluate many integrals. Till now what we have seen is that through the Riemann sum we have evaluated integral of some polynomial up to x q and so on and so forth, but now the whole whatever we did in class 12, now this integration makes sense. So, we can talk of the definite integral through the fundamental theorem of calculus. So, example, as we know that if you take 0 to x sin t dt. Now, what is the antiderivative of sin t? Is the minus of cos t. So, that is minus of cos t and then this is 0 to x, which is equal to 1 minus of no, yeah, 0 to x if I am taking, then the cos 0 is 1 minus of cos x. So, that is fairly easy. So, in that case now we can compute various other things, suppose 0 to 2 e to the power t dt exponential function, then we know that the antiderivative of e to the power t is nothing but e to the power t. So, this is e square minus e to the power 0, which is equal to e square minus of 1. And similarly, if I look at the 3 to 6 dx by x, now we know that the logarithm is the function which is differentiable, that is what we had seen earlier on the interval open interval 0 to infinity. So, now in 3 to 6 this is differentiable, therefore, the antiderivative of 1 by x is nothing but logarithm of x. So, this is ln of 6 minus of ln of 3. So, you can simplify it further. Now, let us get into the continuity of what we have imposed the condition that the small f is continuous. So, now consider capital F of x, this is equal to x square sin 1 over x, x not equal to 0 and 0 if x is equal to 0. This what we have seen is that is a differentiable function earlier, and so this derivative we have computed, it is going to be 2x sin 1 over x minus x square into cos 1 over x into 1 by x square. This is what it is. So, this is if x is not equal to 0, that is equal to 2x sin 1 by x minus cos 1 by x if x not equal to 0. Okay, so, this is 1 over x. So, now if I make the change here, if I take it to be x square, then what you are going to get? So, this is what we are going to get is x square and then this is minus of 2 by x cube. Therefore, this is also differentiable like the way we had defined earlier, and this is going to be 2 by x cos 1 by x square, 1 by x square, 1 by x square. As you can see that around 0 this f prime is unbounded, and we do not have any prescription of Riemann integration for unbounded operator. Therefore, this f prime is not going to be an integrable function. So, it is we cannot actually assume automatically that f is differentiable, then f prime is integrable. That is also not true as what we have seen. However, this theorem is true, the statement. For the sake of completeness, let me just state the result. The result which is true is that let f from a b to r be a Riemann integrable function and f be any antiderivative of f, then integral a to b f b a f t dt, this is equal to f of b minus of f of a. So, this is true, I am not going to prove this, but we can drop the continuity of small f, but we cannot get away with that small f is Riemann integrable. It may happen that the derivative of a function may not be Riemann integrable. So, that is the natural question which lead to the further studies is that what is the condition then you can impose on f such that f prime will automatically be integrable. So, let us keep all those questions for our future study. Okay. So, this is what is the second fundamental theorem. So, now next what we want to see is the very powerful tool to compute Riemann integration, that is by integration by parts. Okay. So, what we have seen, let h of x equal to f of x g of x, and f and g both are differentiable function. Then what we know is that h prime of x is equal to f prime of x into g of x plus g prime of x into f of x. Okay. So, therefore, if you take the integral, on both the sides, integral of h prime of x dx, this is equal to integral of f prime of x gx plus integral over g prime of x f x. Now, we know by the fundamental theorem of calculus how to, if our h is a nice function, then how to compute h prime, integral over h prime. So, we can actually write down, left hand side is known. So, we can, if we can compute one of the right hand side, then the other one we can compute it easily. So, now the theorem is that let f g be differentiable and f prime and g prime continuous. Then we know that f g, f prime, g prime, all of them are Riemann integrable function, and the product f prime g, g prime f, because they are Riemann integrable function. So, what we get is that a to b f of x of g prime of x dx, this is equal to Look at the right hand side, this is nothing but the derivative of the product. Therefore, this is going to give me the evaluation at B and at A of f g. So, this is equal to f b g b minus f a g a and then minus of a to b f prime of x g of x dx. This is what is by integration by parts formula. Okay, so, some example. Now, 0 to pi by 2, let us say x sin x dx. So, here you can take your f of x, this is equal to x, and g of x you can take it to be minus of cos x. Therefore, g prime of x is equal to sin x. Therefore, this is just in the form of the left hand side. So, integration by parts formula will tell us that this is equal to f of pi by 2, that is pi by 2 into minus of cos pi by 2 is 0, minus f 0 is 0 and cos pi by 2 is 1. So, this is turns out to be 0, then minus of integral over 0 to pi by 2 and f prime is 1 and g prime is g of x is equal to minus of cos x. This is equal to plus 0 to pi by 2 cos x dx, which is equal to sin x, which is evaluated at 0 to pi by 2 by the fundamental theorem of calculus. So, this is equal to 1. So, this is there are several useful integration can be calculated through this integration by parts. I would definitely urge you to find something like this. You can actually show that integral of sine to the power n x dx. This is equal to minus of sine n minus of 1 x cos x by n plus n minus of 1 by n integral sine n minus of 2 x dx. Okay. Application of integration by parts you can see. Now, there are okay. So, our aim is to calculate the integration. So, we know that if we can determine antiderivative, then we can compute the integral. It may happen, the cases can occur where it is extremely difficult to compute the antiderivative. Suppose for example, f of x is equal to e to the power x square, simple function. So, now one would like to compute the antiderivative. Well, it is difficult to compute the antiderivative of this. Then in those circumstances, what we are going to do? Let us see that what is our Riemann integral is from the first principle. Riemann integral is saying to be is the sum limit of the Riemann sum. So, essentially what we have seen that f of, and if f is given to us, suppose f is a continuous function or someone had told us that f is Riemann integrable, then what we know is that this is going to be equal to limit n goes to infinity b minus of a by n summation over k from 1 to n f of some c k, where c k lies between the partition this is the Riemann sum. What we have all the liberty to choose the c k. Now, in a sense what we are saying, the limit means for large n this integral f of x dx is pretty much close to b minus of a by n this is what it is going to approximate our integral. Now, what we have seen is that there are various way we can approximate the integral. You choose the left hand point, you choose the right hand point, you choose the middle point, you choose any arbitrary point of whatever is useful for us depending on the situation. Now, let us try to see pictorially. Suppose we have this. Now, let us take a partition x n. Now, this is the equal partition what we have taken. So, these are all b minus of a by n, each of them they are equal. My figure may be x n, we can take it to be little further down, here is x n, then they become equal. Okay. So, another way of looking at it to find the approximation is that let me join this line and let me join this, join this and join this. Now, what in this particular case I can compute the area of these regions and then I go smaller and smaller, and what is the shape of this? So, this is nothing but a trapezium. This trapezium, then what is the area of this trapezium? This area is, this is the height, and then the half of the sum of the parallel side. Now, height is what? Height is b minus of a by n, because each of this is b minus of a by n. Now, what is this parallel this, what is this length of this? This is nothing but f of x naught, and this is f of x 1, this is f of x 2, like this, so on and so forth. So, now this is f of 1 half of f of x naught plus f of x 1. Now, I compute this. So, if I add, then this is again b minus of a by n half of f of x 1 plus f of x 2, and this third is b minus of a by n 1 by 2 f of x 2 plus f of x 3, and this one, the last trapezium in this picture is so. If I make my partition such that the distance length of equal length x k minus x k minus of 1 is large. So, essentially this is also going to approach the Riemann integration. So, what is this? This is nothing but b minus of a by n if I take and 1 half common, this is equal to f of x naught plus this is f of x 1 plus f of x 1, that is 2 f of x 1 plus 2 f of x 2 plus 2 f of x 3 plus f of x 4 for this particular picture. Now, in general, so this is what we call this as a trapezoidal rule. So, this says that so trapezoidal rule this is integral over a to b f of x dx. This is approximation to some T n which is equal to 1 by 2 of b minus of a by n, and then this is equal to f of x naught plus 2 f of x 1 plus 2 f of x 2, this goes dot 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 plus 2 f of x n minus of 1 plus f of x n. This is what is the trapezoidal rule. In other words, this is also equal to summation 1 by 2 b minus of a by n k from 1 to n f of x k minus of 1 then plus summation over k from 1 to n f of x k. That is what the area of the each trapezium, and then you take the sum. This is half times this plus this f of x k minus 1 plus f of x k is the area of the each trapezium in the region x k minus 1 to x k, and you add it up, then you approximate this. This is the trapezoidal rule. So, some of the example, let us try to find out some example of the trapezoidal rule. Let us get okay. So, let us compute for let us give in for a simple case of to demonstrate f of x equal to x square. So, here and we are interested in from 1 to 2. We know how to compute this Riemann integration, but let us apply the trapezoidal rule for this known function, and let us try to see that how much mistake we are making. So, let us consider fix. So, this is and this is 1 and this is 2. So, we want to calculate this integral x square. So, fix let us say n equal to 4. Therefore, b minus of a by n, this is equal to 2 minus of 1 by 4, which is equal to 1 by 4. So, the area T, this by if I calculate the trapezium. So, this is equal to 1 by 2 into b minus of a by n is 1 by 4, and then f what are the x naught? X naught is equal to 1, and then x 1 is equal to 1 plus 1 by 4, x 2 is equal to 1 plus half, x 3 is equal to 1 plus 3 by 4, and x 5 is equal to 2. So, this is 1 square plus 2 into 1 plus 1 by 4 square plus 2 into 1 plus 2 by 4 square plus 2 into 1 plus 3 by 4 square plus this x n will take no 2, only 1 is going to be there. So, this is going to be 2 square. So, if we compute a simple computation is going to give us 75 by 32. Now, let us see how much error we are committing. If I calculate, what we know is that 1 to 2 x square dx by our fundamental theorem of calculus, this is x cube by 3 1 to 2. So, which is 8 by 3 minus 1 by 3. This is 7 by 3. Now, so now if I get 75 by 3 minus 7 by 3, then this is equal to 75 minus 75 by 32, 3 is 225 minus 32 into 7 is 224 divided by 96, which is equal to 1 by 96. You see, even just by taking 4, what we are getting is that we are getting the error margin of almost 0.01. So, up to the first decimal we are getting it correct. So, if we take little more, then obviously what we are going to get a better estimate. So, let us just let me just write down the error term for this trapezoidal rule, and which I am not going to prove it. So, if f double prime is continuous, then it is bounded, of course, f double prime of x is less or equal to m for all x, then this error, which is equal to a to b f of x dx minus of t, this is the mod, this is whatever the t is, the you fix a n, then you compute with the areas of the trapezium. So, this is going to be equal to b minus a whole cube by 12 n square into m. Whatever this number, this requires lot of this requires a proof. I am not going to give you, but for the time being, let us just assume that this is the error. Now, if you calculate in your previous example, then this E t is also going to be equal to less or equal to, because if you calculate the f double prime is nothing but 2, right, x square. So, if you compute that, this is 1 by 12 into 1 by 16 into 2, which is equal to 1 by 96. In fact, in this case, this is going to be error is precisely matching with this, but it may not. And as you can see, this error is an upper bound. So, you can control the error up to this. You have to, if you take n large, as you can see that the error is going to be small and small. So, that is what is the trapezoidal rule, and there can be other method in which we can approximate, which may be easier for us. So, we are going to take it up in the next lecture. Thank you.